Hi, welcome to the third and final video over topic 10.1, the introduction to organic chemistry. And really, by the time you have a solid understanding of all the concepts in 10.1, you are well set up for understanding all of topic 10 or organic chemistry at its introductory level. So aromatic compounds come up in 10.1, and really IB does very little with this, but when you have any carbon backbone with 4 or more carbons in it, they typically are in a straight line, or some branch chains, but it's also possible with 4 or more carbons in your backbone that they could form a circle, and those are called cycloalkanes. And so they're also referred to as aromatic compounds when they contain benzene. That's a whole special category of cycloalkanes. And so again, IB doesn't do much with it. A little bit comes up on some of the worksheets that I handed out in class, but really the only reason for IB mentioning it is because of this idea of a benzene ring. And a benzene ring, if you've heard of benzene, is 6 carbons in a ring or a hexagon with alternating double and single bonds, plus, and this should be just 1 hydrogen each on them. So the formula is C6H6. It's a totally two-dimensional structure, just like trigonal planar molecules such as BF3. So an important one is TNT, is because it's a benzene ring with some substitutions on it. And as we move into topic 15 on medicine, you'll see a lot of medicines have the benzene rings or other rings on them, these cycloalkane groups, and a number of substitutions will be made on the hydrogen, and that's what makes pharmaceuticals very similar to each other, and yet it changes it just enough in case somebody has an intolerance or an allergy to it, or if there's a bacteria that's no longer affected by it, they can make a substitution and actually make a new chemical that will have very similar effects but trick the bacteria or your allergy or whatever it is. So before I move on, I just want to draw what benzene looks like. Again, it's C6H6, and it's 6 carbons in a hexagon. So something like this, and then each one has a hydrogen attached to it. And then the reason there's only 1 hydrogen attached to each, my board isn't quite lined up here, so try to get it on there, is because there's alternating double bonds here. So it's a double, then a single, then a double, then a single. And if you remember resonance from back in HP chemistry, these double bonds this double bond could just as easily be over here. This double bond could as easily be there. This double bond in the next spot. So often they draw benzene. And I apologize, I'm right by the wrinkle in my board, so let me move it down here. They often draw benzene like this, or they draw different cyclo groups, and the assumption is that you know that where 2 lines meet, there's a carbon there. There has to be a carbon there because 2 bonds don't just form on their own. There has to be an atom in between bridging them. So they draw it like this, and then they either draw in the alternating bonds, or they also show the resonance by just drawing a circle in here to let you know. So those are all representations of benzene. I notice my first one's a little sad with my squiggly lines in there, but hopefully you get the idea. So just recognize benzene, recognize the idea that these could be in a circle, and don't expect too much of that from IB on the test. So structural isomers. These are really a big deal because it gives us such a huge variety of chemicals that are just slightly different from each other. So they have some similar properties, but they also have their own distinct chemical and physical properties, so they have their own name. So again, it's compounds with the same molecular formula, but a different arrangement of atoms. And we looked at these a little bit in the earlier videos for 10.1. And the longer the carbon chain, the more isomers that are going to be possible, and that goes up exponentially. You know, you get to butane being the first one with any isomers, and all of a sudden, as you get to hexane and heptane, you got lots and lots of isomers. And another thing to keep in mind is that usually branching makes it act like a smaller molecule. Even though the mass hasn't changed because the formula is the same, it makes it behave as if it's smaller. And that's because the branches keep neighboring molecules from getting too close together and tangling, and it prevents more van der Waals forces developing. So it's going to keep its lower volatility. It's going to have a lower viscosity, a lower density, a lower boiling point. So it's going to maintain more of the properties that you would expect from a smaller R chain in the backbone there. And just one thing IB points out, this is important as far as high octane gas. Branch chain isomers are far better, and that's why they give an octane rating number on there. It's giving you an idea of how much branching is in your octane versus how much straight chain there is. And that's something they can control at the refinery. So before we move on here, I've got a question for you. It says, draw 2,2-dimethylpropane and write its condensed structural formula. So this is actually an isomer of butane because there's going to be a total of 4 carbons. I know that because methyl contains 1 carbon and propane contains 3 carbons. And so if I start from the end, I've got 3 carbons on here for my propane. The 2,2-dimethyl means there's a CH3 group off of the second one, and there's 2 of them. So there's 1 off each side. Let's see if I can improve that a little so you can read what it is. And then to finish this, then I need to saturate the remaining 2 carbons with the appropriate number of hydrogens. This is a hydrogen up here. And so then my condensed structural formula would be CH3. And then I would write C to show that that carbon is there. And then CH3 3 times. Okay, as that's sinking in. A little more on structural isomers. This is just kind of some of the international mindedness that IB likes us to bring in. Tetraethyl lead was something called leaded gasoline. Tetraethyl lead was added to gasoline from 1923 to 1986. So yes, I'm old enough that I remember leaded gasoline. And it was added to make gasolines perform better. They burn smoother. It eliminated this idea of pinging. If you ask your parents, they maybe remember it. But of course, that means we have lead all over our air and soil. It's ended up in our water supplies. They dig up soil when they were doing construction projects along these freeways that have been here for a long time. There's lead in those soil samples. And so it's created all kinds of environmental problems because we now know lead's not a great thing to have in your environment. And ironically, the guy who came up with the idea of leaded gasoline, a fellow named Thomas Midgley, a name like Midgley, we should have just known he's going to be trouble. He also came up with the idea of CFCs, which are chlorofluorocarbons, and they were used to develop aerosol. So our first hairspray that was an aerosol and aerosol paints, what we call spray paint, that was all thanks to Thomas Midgley, but that ended up destroying the ozone. So he came up with 2 huge chemical advancements that seemed like great things at the time, and both ended up having just huge environmental implications. So kind of ironic the same guy came up with both of those. And even more ironic, at least to me, is that he died at age 55 before he realized the damage of his 2 big chemical discoveries. And he actually died because he strangled himself in this invention of ropes and pulleys that he had developed to get him out of bed after losing use of his legs due to polio. So the guy invented a lot of stuff, but he was just kind of doomed, it seemed, right from the beginning. But before I go on, I just want to look at this idea of tetraethyl lead. When you see a name like this, you should be able to come up with the formula because lead is the root or the stem. And tetraethyl means there's 4 ethyl groups attached. So an ethyl group is CH3CH because it's carbon, CH3CH2. So then there'd be another one down here, CH3CH2. There'd be another one here, CH3CH2, and another one here, CH3CH2. And if you look, the idea of 4 ethyl groups bonded to lead really isn't so strange because lead is also in the same family as carbon. So it too can form 4 bonds. And then to finish up this very long introductory section, a couple more things. Is this idea of classes of compounds. Compounds are described whether the carbon atom is primary, secondary, or tertiary, and it's really about how many other carbon atoms are attached to it versus how many functional groups or substitutes are attached to it. So a primary carbon is a carbon attached to a functional group and at least 2 hydrogen. So this is going to be, a primary carbon is going to be one of the first carbons. It has to be the end of the carbon chain. So I think of the primary carbon as being a first carbon. So an example of this would be if I had methanol, COH, it has at least 2 hydrogens. In fact, it has 3 hydrogens attached to it, and it's got an OH group. So that's a primary carbon. A secondary carbon is a carbon attached to a functional group plus 2 alkyl groups. 1 hydrogen, 2 alkyl groups, but I focus on the 2 alkyl groups here because it's going to be attached to at least 2 other carbon groups. So now I've got a carbon. It's got to be attached to at least 2 other carbons. So I'm going to make this one a CH3, this one a CH3. I'll make a hydrogen here, and there's my functional group. So that would be, this one here is my secondary carbon. And then a tertiary carbon is truly in the middle. It's a carbon attached to a functional group plus 3 other carbons. So primary carbon is the first carbon in a chain. Secondary is a carbon attached to 2 other carbon groups. And a tertiary is attached to 3 other carbon groups. And by carbon groups or alkyl groups, I mean not just another carbon in the chain, but 2 branches or 3 branches. So for this one, I'm going to have carbon, I'm going to have CH3, 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 and then my OH group attached. So this makes it my tertiary carbon. Okay, so primary, secondary, and tertiary carbons, they're referring to just 1 carbon within a compound, and that's how you determine which is which. And then to finish up, trends in physical properties. Homologous groups have similar properties, but they tend to show gradation or an increase when you increase the number of compound atoms. So volatility is how easily a substance changes to a gas. It's not how explosive it is, but it's how easily it evaporates or changes to a gas. So a longer carbon backbone is going to increase the boiling point, and if it increases the boiling point, that decreases the volatility. Now, if it's nonpolar, it will decrease the volatility less than if it's polar. If it's polar, then it will really decrease the volatility because now you're going to have strong intermolecular forces plus an increase in those intermolecular forces. So typically the most to least volatile family, so most volatile means evaporate the easiest, have the lowest number of forces between them, are alkanes and something called halogenoalkanes. It's just an alkane with at least 1 halogen in place of a hydrogen. And then aldehydes and ketones, which just have double bonded oxygen. And then the most volatile, or I mean the least volatile, are going to be alcohols and carboxylic acid because they both contain a hydroxy or OH group with that hydrogen bond. So they're going to be the most polar. And then solubility in water, we see the opposite trends because water is highly polar. So longer carbon backbones are going to be nonpolar, so it's going to decrease solubility in water, which actually that's same as volatility, it decreases. But now polarity is a plus, so that the more polar the group, the more soluble it's going to be. So now your alcohols and carboxylic acids are going to be highly soluble in water, the most soluble. And also fairly highly soluble are going to be your aldehydes and ketones because they're at least polar with the oxygen double bonded. And then your alkanes are going to be, your nonpolar ones are going to be the least soluble. So both length and the functional group are going to affect physical properties of volatility and solubility in water.